Good afternoon. This is my solution for bonus problem number 2, dynamics. As illustrated here, we have a double inclined plane with a mass sitting on each slope. These two masses are connected together by a string of fixed length which runs over a pulley system situated at the apex of our double inclined plane. Now these masses are able to move freely up and down their respective slopes without friction under the influence of Earth's gravity. We've also been given the condition that mass number 2 is greater than mass number 1. Now the first part of this problem is to express the string tension T as a function of the masses and the angles. Now as the two masses are connected together, they will both move at the same time with equal acceleration, and the string tension will also be equal on each side of the pulley. From this force diagram, we can see that the force trying to pull mass number 1 down the slope is equal to m1 times g times sine of alpha, which I've denoted here as F1. And the force trying to pull mass number 2 down the slope is equal to mass number 2 multiplied by gravity multiplied by sine beta, which I've denoted here as F2. And as I've already mentioned, both these masses are connected together by a string, so our acceleration for both blocks will be equal, and the string tension for both blocks will also be equal. Now in order to establish what the string tension is, we first need to apply Newton's second law, which states that the sum of all forces equals mass times acceleration, or F equals ma. Now for mass number 1, as its mass is smaller than mass number 2, we can make an assumption that it is being pulled up the slope. And therefore, we can work out from there that our sum of all forces is going to be our force tension, number 1, which is pulling it up the slope, minus the force trying to pull it down the slope, which is m1 times gravity times sine alpha. That gives us our net force here. And from this we can rearrange our force equals ma equation so that we can find out what our acceleration is for mass number 1. So we divide both sides by mass 1. We end up with acceleration for mass number 1 is equal to force tension 1 minus mass 1 multiplied by gravity multiplied by sine alpha, all divided by mass number 1. Then we can do the same for mass number 2. However, once again, based on our previous assumption that mass 2 is moving down the slope, our sum of forces will be mass 2 multiplied by gravity multiplied by sine beta minus our force tension, which is trying to pull it back up the slope. So that's what our sum of our forces is going to be. So our mass 2 multiplied by our acceleration is equal to mass 2 multiplied by gravity multiplied by sine beta minus our tension force. We'll divide both sides by our mass. We end up with our acceleration is equal to mass 2 multiplied by gravity multiplied by sine beta minus our force tension, all divided by mass 2. And as previously stated, our acceleration is equal for both sides. So now we have two equations for acceleration, and once again, because what we can do now is combine these two equations and work out our tension from there. So from our two equations, if we multiply both sides by m1 and m2, we end up with, on the left hand side, mass 2 multiplied by force tension 1 minus mass 1 times g sine alpha is equal to mass number 1 multiplied by mass 2 g sine beta minus force tension 2. If we expand the brackets on both sides, we end up with mass 2 multiplied by force tension minus mass 2 times mass 1 multiplied by gravity sine alpha is equal to mass 1 multiplied by mass 2 multiplied by gravity sine beta minus force tension multiplied by mass number 1. From here we can add force tension 2 multiplied by 1 and mass 2 mass 1 g sine alpha to both sides of our equations. And from there we end up with mass 2 multiplied by force tension plus mass 1 multiplied by force tension excuse me, is equal to our mass 1 multiplied by mass 2 multiplied by gravity sine beta plus mass 1 times mass 2 times gravity times sine of alpha. Now, as force tension 1 and force tension 2 are equal and mass 1, mass 2 are common, we can tidy up both sides of the equation. So we end up with force tension is equal to mass 1, force tension multiplied by mass 1 plus mass 2 is equal to mass 1 times mass 2, all multiplied by g sine alpha plus g sine beta. If we divide both sides by our mass, we come up with our equation for string tension, which is force of our string tension is equal to mass 1 multiplied by mass 2 multiplied by g sine alpha plus g sine beta, all divided by mass 1 plus mass 2. Now, for the second part of this problem, we're required to determine a condition for which both masses are at rest or uniform in motion. Now, in our first diagram, a condition for which the masses would be at rest would either be when mass 2 has reached the bottom of the slope here and cannot move any further, or if the string was not long enough for that to allow this to happen, then motion would cease when mass number 1 came to rest against the pulley. Another condition that would ensure that the masses are at rest is if there was sufficient coefficient of friction between the masses and the slopes such that our mass times gravity times our sine theta, or our pulling forces, was insufficient to be able to overcome the coefficient of friction. And uniform motion is defined as the motion of an object, or in this case, two objects, in which the object travels in a straight line and its velocity remains constant along that line as it covers equal distance in equal intervals of time, irrespective of the duration of time. And since our masses are tethered together by a string, any motion experienced by one mass would be experienced uniformly by the second mass. Thank you.